Okay, so today we're going to be talking about free-falling objects and what forces the object experience when it's falling. So if you can picture yourself jumping and maybe on a trampoline and you're coming down through the air. Well, the only force that acts on you is the force of gravity. Now we do have air resistance that's going to be working on you as well, that's going to be pushing in the backward way, but right now we're going to eliminate air resistance and assume that this is falling with no air resistance. So the only forces acting on are the force of gravity. Well, today what we're going to do is we're going to find out, well, what is that force of gravity? So if we use Newton's first law, we can determine what F of g is equal to. So we know the acceleration when something's in free fall is gravity, negative 9.81. We are given the mass of the object, and what we're trying to find out is the force of gravity. So we know that the F net in this case is just force of gravity down. And we said from the previous lessons that the force net is equal to the mass times the acceleration. So Fg equals mass times, we're going to replace the acceleration with the gravity, and now we know that F of g equals mass times gravity. And this is the case all over. If we go to the moon, the only thing that changes is the value for gravity. If we go to the top of the Himalayas, the only thing that changes is the force of gravity. I'm sorry, the value for gravity. It's no longer 9.8. So in this case, we have F of g equals mass times 9.8 meters per second squared. And the reason why we have a negative is you can see here that it's pointing down, and that makes it negative. So now we know this information and we can solve some problems. Okay, so our first problem here is we have this guy Arnold, and he needs to lift a rock. So he's going to be lifting this rock up. He exerts an upward force, which is the force that his hands produce onto the rock, of 502 newtons. What's the rock's acceleration? So we start, the rock is at 0, and he's going to be accelerating, and he's going to be lifting this rock. So the given is the mass of the rock is 35 kilograms. He needs to lift a 35 kilogram rock. He exerts an upward force of 502 newtons. So the force of Arnold is 502 newtons. What is the rock's acceleration? We're looking for A. Okay, so here's my picture of my rock. The forces that are acting on the rock are the force of gravity down, the force of Arnold pushing up. Okay, so we know that the net force has to be the force of Arnold minus the force of gravity. So the force of Arnold minus the force of gravity, and we know now from the previous slide that the force of gravity is the mass times the gravity. Force of Arnold is 502, and that's from right here. The mass is 35 kilograms. We know gravity is 9.8. Now we don't put negative 9.8 because the negative is already in here. Okay, so we have 502 minus, if I multiply 35 times 9.8, I get 343. 502 minus 343 is 159 newtons. Well, that is our F net. That is not the answer we're looking for. So now we have to find the rock's acceleration. We're going to go back to Newton's first law that says acceleration is the net force over the mass. Well, we just calculated the net force of 159 newtons, and we know the mass. So the acceleration is 159 divided by 35. Our acceleration is 4.54 meters per second squared. That is the acceleration on that rock. Okay, so we're going to talk about something else, and this is called the apparent weight. And apparent weight is just what is the felt weight. So if you can kind of picture yourself riding in like the Tower of Terror at Disney World, or going down a roller coaster or up a roller coaster, you feel different as you're going down. As you're going down, you feel a little bit heavier, and as you're going up, you're feeling a little bit lighter. Well, that feel of your weight is what's called the apparent weight. So if you're in a swimming pool, you feel lighter, even though you really are the same mass and the same weight. Nothing has changed. It's how you feel, that feel. So we have apparent weight as a force exerted by a scale. So if we were to take a scale and put it underneath a swimming pool and you were to stand on it, it would not read your weight that it would be inside your bathroom. And that's what we're looking at, the apparent weight. So here's a girl standing on a bathroom scale. This is a bathroom scale, and we're only going to take the girl right now. What are the forces on her? Well, she has this apparent weight, which is really the normal force. Okay, you can see that that's going to be the force that the scale puts onto the girl. And she also has the force of gravity. In this case, The force apparent minus the force of gravity is your net force. And hopefully, if your scale is working correctly, these two are equal. Well, now what happens if we take the same girl on the bathroom scale and we put her in a hot air balloon that's moving up? So what do you think you would feel? If you can kind of picture yourself going up in a hot air balloon, are you going to feel lighter or heavier? So if you can think of it opposite, what would it feel like if you were going down? Well, if your body's here and the balloon's falling down, then you're going to actually feel a little bit lighter. Okay, so if you're going up, you're actually going to be feeling a little bit heavier, so your force of your weight and the balloon is pushing against that, which is going to create an apparent weight that's heavier than what you normally weigh in the bathroom. So now what we have is we have the same scale, the F apparent, and we have the force of gravity. So our net force, once again, is the apparent weight minus the force of gravity. But our acceleration now, we're going to bring that into play because this balloon is accelerating upward or downward. Up here, we're not accelerating. We're sitting in our bathroom. Here, we're going to have an acceleration, and so you can see that our acceleration weight is going to be the apparent weight minus the force of gravity, which is going to give you a different feeling divided by the mass. Well, let's try an example, and this will help make a little bit more sense. So we're going to take the same scenario of somebody in a hot air balloon moving upward. So this hot air balloon is going to be elevating upward on a bathroom scale. Well, what does the scale read as you're going to be moving upward? Is it going to be weighing, are you going to weigh more or less? Okay, so the way that we work this out is we're given a mass of 8 kilograms. Now, this is what I'm giving you. The balloon is going to accelerate upward at 1.25 meters per second squared, and what we're looking for is the reading of the scale, or the apparent weight. So we know from Newton's first law that the acceleration is F net, the net force, over the mass. So I'm just going to do a little bit of cross multiplying here, and I'm going to say A times M is equal to force net. That's right here. M times A is force net. Well, we know that MA, with the net force from that balloon that's going up, is F apparent minus FG. And this is from the previous slide. Okay, well now I'm going to plug some things in here. I'm looking for F apparent, so I'm going to add FG to both sides. So I have F apparent equals MA plus FG. Well, M is 80 kilograms, that's given. A is 1.25 meters per second squared, and that is also a given quantity. Plus, well, we know Fg is mass times gravity, and mass is given over here, and gravity is 9.8. The reason why we don't include a negative here is the negative shows up right here. So we had negative 9.8 over here, and we moved it to the other side over here, which makes it positive. So our F apparent then is 100 newtons plus 784 newtons, which means it's 884 newtons. So our F apparent is larger than what our mass would be if we were to weigh ourselves in the bathroom. And that makes sense, because as you're going up in an elevator or a balloon, your mass gets heavier. Or your mass stays the same, but your F gravity gets heavier, and so you have an apparent weight, or the weight on the scale, that's going to be larger. Okay, don't forget we have an Edline assignment to do tonight, and tomorrow we'll do a lot more of these problems in class, and hopefully you'll have a good evening, and we'll see you tomorrow.